Hi, I'm Sala. In this first video, we are going to address how to model a tubular heater via finite element methodology. We'll discuss the fact that we can split the heat exchanger, the tubular heater, in several elements, as shown here. So if we address the modeling of each of them, we can have a better approximation to the partial differential equation. Actual simulation of that finite element model will be addressed in forthcoming videos. In this video, we'll make a quick summary review of the models we discussed in detail in other videos of this collection, and we'll use the first order lumped parameter models as the basic building block for the many finite element model, and we'll see how to build such models with the symbolic toolbox of MATLAB. Our tubular heater or tubular heat exchanger will have the data that are shown here: total length, cross-section, bar kappa will be the heat conduction losses per unit length. Here we have the volume. C will denote the specific heat capacity. It will just be water, and rho fluid density, also water. And we'll store them here for later numerical simulation, because for the moment being, we will use rho and C as symbolic variables in our manipulations. Some models require a nominal flow operating point, and we'll set that to 0.2 liters per second. So let us quickly review the many modeling options we saw in earlier videos. We are assuming outside temperature to be 0, so our temperature units are actually increments with respect to the environment in which this heater is placed. First, the ground truth best model is the partial differential equation. Okay, it's the partial differential equation if we have, laminar flow, no steering, and there are no vertical temperature gradients, and we neglect heat capacity of the pipe. We will just assume that this is the most exact model, but in stringent applications, we might even need to further complicate it. But okay, let's keep it simple. So we have this PDE, and due to this product, it's nonlinear if flow is not constant. However, if flow is constant, this PDE is a linear one, and we can solve it. And for instance, using Laplace transforms, we may obtain an exact constant flow model in transfer function form. So this is the transfer function that multiplies increments in heating power, and this is the transfer function that multiplies increments in inlet temperature, with these values of A, B, phi, etc., depending on physical parameters. The details are in other videos. If we set this to 0, then we get what's called the steady state ordinary differential equation, because then only derivatives with respect to x remain. The steady state model can be written as this, and for uniform heating along the pipe, it can be shown to have this solution. So when thermal equilibrium is reached, the temperature profile along the pipe will have this expression, and the outlet temperature, it will have this expression in which we have static gain that multiplies the inlet temperature and another static gain that multiplies the heating power per unit length. So this two-gain model is the linear approximation for constant flow in equilibrium. Of course, it's coincident with setting s to 0, so these exponentials are unity in the Laplace transform representations. Importantly, in slow applications, this is the most frequently used model. If you come from an undergraduate heat transfer course, maybe this is the only detailed equation you have seen about heat exchangers, and it's for one reason, because it's the most frequently used in applications. This lambda and these gains will be used later on, so we will encode them in this code. Importantly, lambda depends on the flow. The slower the flow, the more important heat loss is. So this is the lambda, and this gain to the inlet temperature here, which depends on flow and length, is encoded in this line, and the gain with respect to the heating power input is encoded in this formula here, depending on flow and length. And I also added this multiplication by 1000 in order to have the heating input in kilowatts instead of watts. In our actual heater with our data, the steady state will have a loss of 34% of the inlet temperature due to heat losses, and the heater will have a gain of 0.97 centigrades per kilowatt. Another issue we discussed in previous videos is that in order to derive first-order models, energy balances deal with the mean temperature, this kind of expression. And if our first-order models wish to correctly emulate the steady-state gains, we can compute this A and B and prove that the average temperature is this linear interpolation between inlet and outlet temperatures in which the interpolation coefficient beta has this expression. So we encode that expression for later use, and in fact, for instance, in our actual heat exchanger, that beta is 0.535. So if we plug that beta in our first-order energy balances, our resulting DC gain will be the same as the stationary model from the partial differential equation. If we have a lumped parameter model, inputs are flow, heating power, inlet temperature, we have this beta, and this is the energy balance on the mean temperature. We will just use the symbolic variable capital T instead of bar T we dealt in the text. So the state equation, the time derivative of the mean temperature, is given by this expression. Or well, we can just move things if we find it convenient, or if our input and heat transfer coefficient are given per unit length, then we get this expression. But as I said, the details are in other videos. But in summary, this is the first order element with a given exponential temperature profile implicitly encoded in beta that will be used as the basic building block for our finite element tubular heater approximation. This is the state equation. We'll later on discuss the output equation. Let us now discuss the many element model in which the whole heater, for instance, we split it in 4 heaters, and we will model each of the 4 sections as a first-order lumped parameter state space model. So in these elements, the flow is the same in all of them. It's a kind of serial interconnect. If we assume uniform heating power, then the heating power Q is the same in all of them. And of course, the length and the volume are just 1/4 of the total length and volume. This is it. Flow is the same. If we have capital N elements, the volume of each element is total volume divided by N. Heating power also divides by N, and heat losses are total divided by N. The interconnection is equal flow, but also the inlet temperature of element 2, let's say, is the outlet temperature of the element 1. So we will set up this equation, except of course for the first element, in which its inlet temperature will be the actual inlet temperature for the exchanger. So it will be an input in our simulation. Boundary condition in PDE jargon, but just an input signal in our latent simulation, that's it. So the block diagram representation will be something like this. Flow enters being the same in all elements. The proportional share of the total power also enters all elements. And then inlet temperature enters in the first element, and its output temperature will reach the inlet temperature port of element 2. The output of 2 will be the inlet temperature of 3, and so on, until the outlet temperature will be equal to the output temperature of the last of the elements. So this is how to conceptually connect the n elements, but of course doing it by hand will be tedious, and we will just carry out a for loop in MATLAB symbolic toolbox code in order to build the whole state space equations for the finite element heat exchanger model. We will just recover the numerical values of heat capacity and density of water, and constant parameters for each element. We will set the number of elements. Here we have 301 elements, let's say. it's arbitrary. We will do simulations with 3 elements, with 100 and 300, the more elements we plug in, the closer we will be to the exact PDE solution, but the longer it will take to compute our simulation. So we get the volume, the share of power, and the share of thermal losses, the loss per unit length times the length of each of the elements. Here we have the length. And if we compute the beta coefficient for 300 elements, it's a very short element, and beta is basically 0.5. It's a linear temperature profile. The overall profile is exponential, but in a very small section, the linear approximation is a very good one. Nevertheless, we can change that beta to whatever value we wish, and we'll see how it influences simulations in next video. So this was the symbolic equation we derived here, but instead of the total heat, we will just put the heat per element, and with the eval command, we will replace numerical values instead of symbolic constant parameters. So the state equation for one element will be this thing, temperature derivative. However, as we'll have many elements, we will need to put an index here for each of the elements, and we need to replace the inlet temperature by the outlet of the previous one. So this needs to be changed. Let us do it with the symbolic toolbox. Also, from the equation that defines the average temperature, as the state equation will provide us with the average temperature, the output equation needs to be solved now here. So solving for T out, we will get this output equation for each of the elements. So it will be something like this in our particular example, let's say. If we change beta, these numbers would change, of course. So we will now create a vector of capital N symbolic variables from T1, T2, T3 up to the last T301. So we are now in condition to build the whole model. We will get N symbolic equations set to 0. And now the first element equations are different because the input to it is the actual inlet temperature. So we only need to replace the dummy variable T by T1 in the state and output equations for the first element, but from second onwards, we need to change input temperature to be the output of the previous element. So we need to substitute temperature 2, 3, 4 by the corresponding symbolic variables T2, T3, T4, etc. And input temperature needs to be replaced by the result of the output equation of the previous element. This is it. So we do the same for the state equation and the output equation of each element. And we go from the second to the last one in this for loop. In that way, we have built the whole model. We have a total of 301 state equations for each element in which we have changed from the template one with the suitable inputs and outputs and states. And those equations will be the ones that will be simulated, numerically integrated by an ordinary differential equation solver. For instance, if we have a look at the first 5 state equations, this will be the first element regarding T1 and of course the actual inlet temperature as input. The second state equation will refer to the evolution of T2 given by this expression, in which instead of the inlet temperature, we have replaced the output equation of element 1 and so on. This will be the derivative of T3, T4, T5, etc. up to 301. And last, the output equations. This will be the output of element 1, the output of element 2, etc., which can be used in a direct way if we want to actually obtain that output temperature, or be kept just for use in order to correctly build the state equations. So for instance, this output of the third element is the one that appears here in the state equation of the fourth element, and so on. So we'll finish it now. Actual numerical computations and simulations will be left for future videos. Thanks for watching.